Okay, organometallic reagents. Very important with organic chemistry. We are going to make a carbon-metal bond. And the reason it's very important is because our metal atoms, usually in organometallic organic chemistry cases, are lithium, magnesium, or copper are the main ones we're going to use. Lithium, magnesium, and copper are less electronegative than carbon. Carbon is more electronegative, which means if we have a carbon-metal bond, the metal is positive, the carbon is negative. Most of the time, up to this point, we've been dealing with positive, partially positive carbons because they've had oxygens on them or chlorines or carbonyls. We've had partial positive carbons. Now we're dealing with partial negative carbons. Carbons that are much more carbanion-like than carbocation-like. And especially if we have alkyl, aryl, allyl, benzyl, sp2 hybridized carbons, these work real nicely. If our R group is a lithium, we call that an organolithium reagent. Makes sense. If our R group is a magnesium with a bromine usually, or a chlorine, we call them organomagnesium bromides or Grignard, because Grignard was the person who came up with these. And if we have two R groups bonded to a copper with lithium, these are organocopper or organocuprates. Note that even though we have two R groups on there, two negatively charged carbons, partial negative carbons, only one R group will get used in the reaction. Only one of these is going to react. Okay, and that's the most important thing here. The carbon-metal bond makes the carbon react like a carbanion. So sometimes people draw them as we drew them here with this carbon-metal single bond here. Sometimes people just draw the carbon with two electrons negative charged in the metal positive charge because organometallic reagents react like carbanions, negatively charged carbons. All right, so how do we make our organometallic reagents? Well, if we start with an alkyl halide, we can react it with lithium metal. And if you remember your electrochemistry tables from Gen Chem 2, you know that lithium metal is very, very reactive. Lithium metal wants to become lithium plus. It wants to lose an electron. It wants to become oxidized, which makes it a very nice reducing agent. If we take CH3Br plus 2 neutral lithium metal atoms, we actually make CH3Li, that lithium is bonded to the CH3, and lithium bromide here. And so that makes our organolithium reagent. We can make a Grignard reagent by taking an alkyl or aryl bromide and just throw in solid magnesium. Yes, you need to shine it up so it's nice and shiny with a little diethyl ether, and you will make the here methyl magnesium bromide. You put the magnesium, which was magnesium in the zero oxidation state, it gets oxidized to the +2 oxidation state and gets inserted in between the carbon and the bromine here. And you need to run this in anhydrous diethyl ether because this is an unstable. RMGX is unstable, and the ether helps stabilize the magnesium. To make our organocuprates, we actually have to start with another organoreagent. You have to first make the alkyl lithium organometallic reagent, and then use two equivalents of that alkyl lithium organometallic reagent plus copper 1 iodide to make our organocuprate here, plus lithium iodide. All right. One that we actually learned of, an organometallic reagent that we learned of way, way back in Chapter 2 was actually acetylide. We recall that if we have a terminal alkyne, the pKa of this proton is 25, which is fairly acidic for a proton on carbon. Which means if we took, say, NaNH2 or NaH hydride or amide ion, recall that the conjugate acid of H- is H2, which has a pKa of about 35. And its going to attack this hydrogen right here just in a simple acid-base reaction to make this acetylide carbanion, and you could have written this as a single bond here as an organometallic reagent. Okay, so we learned about these organosodium reagents, especially these organoacetylene reagents, these acetylene or metal acetylene reagents, because of the relative acidity of that hydrogen. We learned about that as just a simple acid-base reaction in chapter 2. Now, when we're looking at the reactions that organometallic reagents do, we're going to start off with reactions that you do not want them to do. Isn't that fun? Okay, everything under 4 here, 4 right there, we don't want these reactions. Let's look at this. If you have CH3Li, this organolithium reagent, and you react it with water, you will make CH4 and LiOH. And then said, well, that's a nice reaction, works really well. But organometallic reagents are expensive. They're very, very reactive. Methane gas is cheap. You can just buy methane gas. What we're telling you is, what this reaction is showing you is, if you have an organometallic reagent and there's any water around, forget about it. The organometallic reagent's immediately going to react with the water to make an alkane and a basic alkyl hydroxide here, which means you no longer have this organometallic reagent that you took time and effort to make. Time, effort, and money to make this. You don't have it anymore if there's any water around. If you have an organometallic reagent, a Grignard here, and there's any alcohol around, yeah, that carbanion is going to attack that hydrogen and make this benzene ring, and you get this beast right here. And no, you don't want to make benzene. You probably started with benzene. Realize you had to make this organometallic reagent. We made it in lab, or we're going to make it in the lab, depending on which semester you're at here. This is made in lab, and it took us time and effort to take bromobenzene and put that magnesium in here to make this very reactive organometallic. If there's any alcohol or water around, boom, you're back to the benzene again. Any acid. Here's an alkyl lithium with an acid, a carboxylic acid. Of course, it's going to react with, take that and make your alkane again, and that's not what you want. So what reactions do you want? You want to run the reaction with your organometallic reagent as a nucleophile. It's a carbanion. It is a strong nucleophile, and it wants to attack, and here's the fun thing, carbonyl carbons. We're going to find of most use with our organometallic reagents when we have carbonyl carbons around, because our carbanion will attack this positive, partial positively charged carbon of the carbonyl, and we form a new carbon-carbon bond. Because this is what we want, we're going to want to attack carbonyls. We have to make sure that when we're doing these reactions, there are no acids around, no alcohols around, no water around. Otherwise, the reactions just will not work. Okay, so let's look at some organometallic reagents and aldehydes and ketones. Here's our nice aldehyde here. R prime means it would be a ketone. And if we took this Grignard reagent or an alkyl lithium, followed by water, 2 reactions, do this do the organometallic reaction first, and then add water later, you convert an aldehyde or ketone into an alcohol, a primary or secondary or tertiary alcohol, depending on what you start with. But the most important thing, R double prime, this alkyl group is now attached to the carbonyl carbon. You make another carbon alkyl group, another carbon-carbon bond right here. Okay, and the mechanism, pretty straightforward. We have a carbonyl carbon, which is positively charged. We have a carbanion, at least it reacts as a carbanion. And so these 2 electrons, very carbanion-like, will attack the carbonyl carbon. Recall that always causes the pi bond to break. Since now we have the bond between R double prime and the carbon, we've got a carbon-carbon bond here and a carbon-hydrogen or carbon-carbon bond here, all fairly strong bonds, no leaving groups. That means that this oxygen, this oxide here, is going to attack the hydrogen of the water, our aqueous workup, and form our alcohol. So we get nucleophilic attack followed by protonation of the alkoxide. So check it out. So examples, if we had this benzaldehyde, hey, our favorite aldehyde, benzaldehyde, if you took ethyl lithium followed by water, you're really just going to put the ethyl group on this carbon and OH here. Ethyl on the carbon, OH. That's a weird way to draw it. So, oh yeah, that looks nice. If here, well, here's our acetylide. You take our acetylide here with the lithium on there. Double bond here will attack this carbon. It'll attack the carbonyl carbon. This becomes an OH. The carbonyl oxygen becomes the OH, and now you've got acetylene attached to that carbon of the ring. Okay. And now you probably all have the same question. Well, that's cool, but what about the stereochemistry of these organometallic reactions? Well, I'm glad you asked, but I bet you figured it out already, didn't you? Because you remembered that the carbonyl carbon is trigonal planar, which means that the organometallic reagent, our carbanion, can attack from the top side or can attack up from the bottom side. So if we have our molecule right here, this ketone that has two different groups coming off of it, propyl and an ethyl. If we're going to attach this methyl group with this organometallic reagent followed by water, we get this tertiary alcohol that has a methyl, that's a 3 right there, doesn't look like it, it's a 3, a methyl, an ethyl, and a propyl group. That is that's a chiral carbon. It's a chiral carbon, which means we're going to get a racemic mixture of the two enantiomers. Every time we make a chiral carbon, not optically active, our product cannot be optically active, so we get a racemic mixture here, which, as we all know, in the world of chemistry, making racemic mixture happens all the time, and we are not happy about it. Racemic mixtures make us frown because we probably only wanted one of the enantiomers. We only wanted one of the enantiomers. Okay. Let's look at a little retrosynthetic analysis here. What we know then is if I have this molecule here, CH3, CH2, CHOH, CH2, CH3, and I'm asked, how did you make that? How could you make this? You can look and say, oh, wait, a secondary alcohol. Secondary alcohols come from the reaction of an aldehyde with an organometallic reagent. Recall, a ketone with an organometallic reagent will give us a tertiary alcohol. But we've got a secondary alcohol. I know I can make this from an organometallic reagent and an aldehyde. And so I realize that my aldehyde is just, okay, this carbon-oxygen single bond here came from the carbonyl, so I'm just going to make that the carbonyl aldehyde with the CH2, CH3 on it. And then I had to attach this ethyl group, so I must have ethyl magnesium bromide or ethyl lithium. Either one of those would do fine. So note, if I said, okay, then how do you make this beast right here, the cyclohexane with an OH off alpha to the cyclohexane and this ethyl group on that carbon here? You might realize, there are two different ways to make this via organometallic reagents. It's a secondary alcohol, therefore I had to start with an aldehyde. My aldehyde could have been this group right here. It could have been the cyclohexane bonded to a carbonyl and an H. Or my aldehyde could have been this group over here, CH3, CH2, C double bond O, H. I have to have an aldehyde. There are two different ways I could have that aldehyde. I could disconnect here and have this aldehyde, or I could disconnect right here and have the cyclohexylaldehyde. So I could have the cyclohexylaldehyde, react it with CH2, CH3, MgBr, Or I could have this aldehyde over here and just react it with the cyclohexane MgBr. Two ways to make it. Which is better? Sometimes it just depends on the reagents you have on hand. So you don't have to buy something. Either one will work fine. Okay. We will continue next time looking at, okay, what if I have a couple of different groups in my molecule that might react with my organometallic reagents, and I only want the carbonyl I want to react? Well, we need to protect it, so we're going to look at protecting groups in the next video.